Section 10.8, we're going to talk about electronegativity and polarity. And kind of the question that's going to prompt this discussion, and the question that we're going to answer through this discussion is, why do oil and water not mix? We've all observed this. Here's a picture. There's oil up here and water. And you've all observed that. They separate. If you look at Italian salad dressing, it's an oil and vinegar dressing. Vinegar is mostly water. And you can shake it up, but then you set it down and it settles. And you've got the oil layer on top and the water layer on the bottom. And it just will not stay mixed. And if you've been making soup or something, all the fat comes to the top and it just stays up there. Why? Why does it do that? Well, there's something about the molecules, particularly the water molecules, that causes them to bunch together and basically push the oil molecules out. They won't let them in. So we're going to investigate what causes that. And we're going to be looking back at our concepts of Lewis structures and molecular shape to understand this. So if we look at the Lewis structure for water, we see that there are single bonds between the hydrogen and oxygen atoms, and that the oxygen has two lone pairs on it. So the hydrogen is bringing one electron and sharing, and the oxygen is bringing one electron and sharing, and so there's this pair of electrons that they're sharing between them. But they don't share equally, okay? Just like if you have the big brother and the little brother and they're sharing a cookie, big brother breaks the cookie and he gives the little piece to the little brother, okay? Because little brother is so clueless, he doesn't understand, he's getting shortchanged. So oxygen and hydrogen are sharing, but they're not sharing very fairly. The oxygen hogs more than its share of the electron pair. So this brings up a concept called electronegativity. Electronegativity is the ability of an element to attract electrons within a covalent bond. So this refers only to covalent bonds. When there's a covalent bond, the more electronegative atom will get more of the electron pair. So in the hydrogen-oxygen bond, the oxygen is more electronegative, and it's going to be more attractive to those electrons, and so they're going to spend more time near the oxygen than they are near the hydrogen. Electronegativity does have numbers associated with it, but it's a relative scale. It was just arbitrarily chosen that fluorine should be 4.0. Don't know why. I think it was Linus Pauling that developed the electronegativity scale. Not sure what his reasoning was, but there it is. 4.0 is the highest value, a little bit like a grade point before all this AP stuff. Anyway, so fluorine's the most electronegative element. And we just said, okay, that's 4, and then we'll measure everything else relative. So let's look at a picture of the oxygen-hydrogen bond. And here we're looking at one of those dot representations and showing the electron distribution. So we see that the electrons, that pair of electrons, is spending more time over here than it is over there. Well, if they're over here more, the electrons have a negative charge, so this end of that bond is going to be slightly negative, and this end of the bond is going to be slightly positive. It's not an ionic bond where the electrons were transferred from one to the other. They're being shared, but they're not being shared equally. So that's why it's not a full negative charge, it's just a partial negative charge. And this uneven sharing results in what's called a dipole moment. A dipole moment is a separation of charge. So this is like the poles of the Earth. One is different than the other. So dipole, there's two poles. We symbolize these with this Greek. This is a lowercase Greek delta. This font looks a little funny. Let's draw you a better one. So that would be delta minus, well, that's not very good either. And that's delta plus. So that's the lowercase Greek delta. We saw the uppercase Greek delta was it's a triangle. The lowercase is like a D with a really bad back. Okay, it's all bent over, hunchback D. So that's what that means. It's a partial positive, partial negative. And we don't really care exactly how partial. It's just less than 1, but more than 0. So I have, of course, a stupid analogy for this unequal sharing business. So I imagine the pair of electrons as being two little boys, and they're neighbors, and they're good friends, so they like to play together. And so one little boy lives at the H house, and one lives at the O house. And they're going to be together, and they're going to be running around the neighborhood, and they're going to spend more time over here than they are over there. Why is that? Well, if you go into H's house, they have a little old television, and they don't have Netflix or anything. They don't even have internet access. They've got a little VCR player and some really old videotapes. And if you're hungry, Mom will give you a peanut butter sandwich, not even any jelly, and a cup of cold water. And so, Mom's real nice and everything, but there's just not a lot going on there. And then next door at O's house, these guys have the big plasma screen TV. They've got satellite with all the channels, and they've got all the gaming systems. And if you say, I think I'm getting a little hungry, Mom will order in pizza for you. And they actually have a soda fountain in their kitchen. So, just anytime you want, there's soda. Where are those two little boys going to spend more time? At O's house or H's house? They're going to be at O's house more, right? It's natural. It's more attractive to them. Okay? So oxygen is more attractive to the electron pair that's being shared in this bond. And so those electrons spend more time over here than they do over there. So it's still sharing, but it's unequal. Do these little boys ever go over to H's house? Yeah, occasionally he needs to get some clean underwear or something and say hi to his mom. But then, they spend more time over here. So it's not like H left his home and left his parents and became adopted by O. That's an ionic bond, where you have a complete transfer. There's still sharing here, but it's not equal. Does that make sense? So more electronegative means more attractive to the electrons. So when we have covalent bonds like that have a dipole moment, unequal sharing, we call them polar covalent bonds. So polar covalent bonds. Did I click that? I did not. Polar covalent bonds. That means that the sharing is unequal. There's a dipole moment. One end of the bond is a little positive. One end of the bond is a little negative. Now, if the electronegativity difference between those two elements is really, really big, then the dipole is greater. If it's really small, then the dipole is small. That partial charge is going to be smaller. If the difference between those two houses were, difference in a brand of peanut butter on the sandwich, it really wouldn't make that much difference, right? And so the smaller the difference in electronegativity, the smaller the dipole moment, and the less polar the bond. The greater the difference, the more polar the bond. Here's a table of electronegativity values. And there might be some homework problems, I can't remember, where you need to refer to this. We're not going to actually deal with the numbers on an exam, but it's helpful to look at them. So here's fluorine, and fluorine has the highest electronegativity. This is the coolest house on the block. This is where all the little electron boys want to go because they've just got everything. They got a bounce house and with those cool water slides in the backyard. It's just awesome. Awesome. It's like going to Disneyland. Okay, and from there, everything else is just not quite as fun in comparison. And there's a trend here. In general, as you go across a period, the electronegativity increases. And as you come down a column, the electronegativity decreases. Okay? So that's following the same as I believe the ionization energy. Yeah, ionization energy increased as we went across and decreased as we went down. I think the best way to remember this trend is to remember that fluorine is the best, fluorine is the most electronegative, and so are you going towards fluorine? Then it's getting bigger. Okay, so if you're comparing gallium and selenium, well, selenium's closer to fluorine, it's going to have a higher electronegativity. And there are some in here, like sulfur and carbon, are different elements, and yet they have the same electronegativity, nitrogen and chlorine. And you can't really just predict by looking at the periodic table which ones are going to be the same. So I won't ask you to do that. If you have two elements that have the same electronegativity, then there's no dipole, because those two houses are identical and the boys go back and forth between them equally. So no difference in electronegativity means no dipole. That, of course, is going to happen when those two elements are identical. In this illustration, we have a chlorine-chlorine bond. Chlorine is the same as chlorine. They have the same electronegativity, and so there's no difference, there's no dipole. So we call this a nonpolar covalent bond. It's covalent because there's sharing, and nonpolar means they're sharing equally. So any bond between two atoms of the same element is nonpolar. So that's an important point right there. We can look at the chart and see whether they're different or not. What I want you to remember is if the two elements are the same, it's nonpolar. We don't need to look at a chart for that. If the difference in electronegativities between the two elements is really big, it's actually an ionic bond, and there's a complete transfer. So what do we mean by really big? Well, we'll look at that in a minute. But this is what you should remember. We learned this back in Chapter 5. We have ionic bonds between metals and nonmetals. So if you look at that and you've got a metal and a nonmetal, you can just say, bang, that's ionic. You don't have to compare the electronegativity differences. So here we have an example of sodium and chloride. Chlorine is so much more electronegative than sodium is that the little boy that lives at the sodium house leaves his family and joins the chlorine family. Okay? These analogies get weird when you carry them out a little farther. When there's kind of a middle difference, that's where we have the polar covalent bond. It's not the ionic bond, because they're still sharing. That little guy still lives at his house. They're still his parents. They're still in charge of him. But he spends more time over at his friend's house. Polar covalent bonds. And so these we're going to see between two nonmetals. And what you should remember is two different nonmetals. Because if the nonmetals are the same, if it's chlorine and chlorine or sulfur and sulfur, then it's nonpolar. There's no difference. If they're two different ones, then I would expect you to say it's a polar covalent bond. So hydrogen and fluorine, we can tell that the fluorine end is more the fluorine end is more negative. It's got the delta negative sign, and this has a delta positive, because obviously fluorine is the closest to fluorine and hydrogen is not as close to fluorine. So hydrogen is less electronegative and fluorine is more. So it hogs the electrons. So of course, we like to quantify things. There's a continuum here. Okay, so you can have a difference in electronegativity of 0 all the way up to a difference of 3.3. And everything in between. And so we tend to call this, because the difference in electronegativity is a lot to say. So we use delta En. Delta meaning change or difference, En standing for electronegativity. So if the electronegativity difference is 0, which by that we mean really small, 0 to 0.4, then we say it's a pure covalent bond. So always when you have two identical elements, it'll be purely covalent, nonpolar. Your book doesn't use it as much, but I like the term nonpolar. Can you have a nonpolar covalent bond between two different elements? Yes, you can. Okay, I pointed out to you earlier, see if I can remember. I think it was nitrogen and chlorine, and carbon and sulfur are different elements, and yet they have the same electronegativity. If you have a chart in front of you, like when you're doing homework, then you should look up the electronegativity values and find the difference and decide based on that. But what I want you to be able to do for an exam is if the elements are the same, it's nonpolar. If the elements are different, then assume that it's polar, okay? Two nonmetals that are different on an exam, I would expect you to say that those are polar. So intermediate difference, 0.4 to 2.0, those are polar covalent. So if you see two different nonmetals, choose polar covalent. A large difference means greater than 2, or 2 or greater. That's ionic. And the way I would want you to identify ionic is when you look at these, if there's a metal and a nonmetal, then call it ionic. Okay? So that's kind of the lower level basic understanding that I want you to have. Looking up the numbers and finding the differences. There may be some homework problems. Like I said, I can't remember what homework I assigned. That was days ago. There may be some homework problems where you have to look at that, and you should be able to do that given the information, but I'm not going to expect you to do that for an exam. So let's look at these. Determine whether the bond formed between each pair of atoms is pure covalent, polar covalent, or ionic. Well, how do we do this? And by pure covalent, we mean nonpolar. Well, between iodine and iodine, what's that going to be? That's got to be pure covalent or nonpolar, because they're the same, right? How about cesium and bromine? We're going to have to look at the periodic table for some of these. What kind of an element is cesium? It's a metal, and bromine is a nonmetal. Therefore, this is ionic. How about phosphorus and oxygen? Without looking at the table of electronegativities, what should we call this? We should call it polar. Two nonmetals, but they're different. Okay? If they're the same, they're nonpolar. If they're different, they're polar. So we just learned about polar bonds, so we also have to talk about polar molecules. You can have a molecule with polar bonds, but that doesn't necessarily mean that the entire molecule is polar. Well, what do we mean by a polar molecule? It has a net dipole moment, which means that the polar bonds add together instead of canceling each other out. And the molecule itself, the whole thing, has one end that's kind of positive and one end that's kind of negative, instead of being symmetrical and uniform. So if we have a diatomic molecule, diatomic means two atoms, right? Two atoms, you only have one bond. So in that case, if the bond is polar, the molecule is polar. But when you have more than two atoms, you have to consider the shape of the molecule and the bonds, whether they're polar or not, because they could cancel each other out. So let's look at how that works. So let's look at carbon dioxide. So here's the Lewis structure for carbon dioxide. We see that everybody's got an octet, everybody's happy, and we learned last week how to talk about the shapes of these and predict shapes. So we look at the central atom and we ask ourselves, how many groups of electrons are there? Well, here's one group and here's another group, two groups. How did two groups get away from each other? They go to opposite sides of the atom. You and your X, whatever, going to opposite sides of the planet Earth because you just hate each other that much and you're trying to get away from each other. So here's a model, space-filling model. Here's the carbon atom, and the oxygen atoms are going to be on opposite sides of it because they're trying to get away from each other. And so we learned that this is a linear molecule. So we've established the shape, the geometry, and now we're going to look at these bonds. Well, carbon-oxygen, is that a polar or a nonpolar bond? Polar, they're different. Which end is more electronegative, oxygen or carbon? Well, we look at the periodic table. Which one's closer to fluorine? The oxygen is closer to fluorine. So the oxygen is more electronegative. O's house is more fun to be at than C's house. Okay, so those little boys spend more time over there. That arrow is another way of representing it. In this bond, this is negative and this is positive. So the oxygen end is more negative because the electrons with their negative charges go over there more. This arrow is pointing to the cooler house, and we put a little plus over here. So this is like the neighbor, and somebody comes looking for these little boys. They say, "Where'd the boys go?" And the neighbor points. They went to that house. So the arrow is pointing to the end where the electrons are more often. Are they always over there? Not always, but your chances are much better finding them over there. So that one, we're pulling the electrons. We think of, or I think of, oxygen is pulling the electrons this way. But there's also an oxygen on the other side, and he's pulling the electrons in that bond the other way. So in this bond, the oxygen also has the partial negative. And so we kind of have this tug-of-war thing going on. So you can imagine this as people playing tug-of-war, where you're pulling on a rope. They don't let kids do that anymore because you could get hurt, right? So here's carbon standing in the middle, and he's playing tug-of-war with one arm with oxygen and the other arm with the other oxygen. And the oxygens are stronger than he is. But are they going to move if they're pulling on each other? Is it actually going to move one way or the other? No. If we had just carbon and oxygen playing tug-of-war, oxygen would be pulling carbon in his direction because he's stronger. He has more attraction. But here you have opposing forces, and so they cancel each other out. Does that make any sense? Does that make sense? So they're canceling each other out. So because those dipole moments cancel each other, then the molecule is nonpolar, even though the bonds are polar. The molecule itself does not have a negative end and a positive end. So we look at this. Why would this end be negative and that end be positive? There's no reason. You could argue, well, the center is a little bit positive and both ends are negative. Well, that's fine, but both ends of the molecule are the same. Polar means that one end is different than the other. If both ends are the same, no matter what they are, it's going to be nonpolar. So that's an example of a molecule that has polar bonds, but the molecule itself is nonpolar. Another way to represent these polar bonds is with vectors. So I drew those arrows, and I said it's like the neighbor pointing. The arrow points in the direction of the negative pole. We put a positive sign, a plus sign at the positive pole. So, some of you like math more than others. And at some point, you were probably introduced to vector addition. A vector is an arrow that has a length, a magnitude, and a direction, and you can add them together. And it's a little bit like people playing tug-of-war. So if you add those vectors together and they add up to 0, you have a nonpolar molecule. If the vectors add up to anything else, then you have a polar molecule. Let's look at water. Water's a little different than carbon dioxide. Although if you didn't look at the Lewis structure, you might not realize that. Okay, They didn't put the lone pairs in here. The Lewis structure for oxygen has 2 lone pairs on the oxygen. Those lone pairs are repulsive to those bonds. When we talk about the shapes, we say that oxygen has 4 groups on it, right? 2 bonds and 2 lone pairs. And 4 groups get away from each other by making that tetrahedral shape. So electron pair geometry is tetrahedral, and then we say, yeah, but those lone pairs are invisible. They're so tiny we can't see them. What's left, and we get this bent structure for water. So water's bent. And here's the space-filling model reflecting that. Because on this side, there's a lone pair, and on the other side, that where we can't see, there's a lone pair. And so those are pushing those hydrogen atoms a little closer together. So when we look at the dipoles in these bonds, we've got this one going this way, and this one going that way. Because the oxygen's more electronegative. We look at the periodic table, oxygen's a lot closer to fluorine than hydrogen is. So the electrons spend more time at oxygen. And so we can think about adding those vectors, or we can think about playing tug-of-war. So here you've got, I'm sorry for the video, but you won't see this. So I'm oxygen, and I've got one hand out here holding onto a rope that hydrogen's pulling on, and the other hand out here. It's not straight out on each side opposing forces like it was with carbon dioxide. They're at an angle now. I'm stronger than they are, and so I'm pulling on this one and I'm pulling on this one. Am I going to be moving and dragging them? Yeah. I'm going to be moving straight back and dragging both of them with me. And so that's how we think about adding up these dipoles. And so there is a dipole moment for the water molecule. This end, I don't remember what color I have going on here, but this end is going to be partially negative, and this end is going to be partially positive. Does that make sense? The vectors don't cancel each other out. They're not opposing each other. These are some common circumstances. We end up with a nonpolar molecule when we have one that's linear, and we've got the same atoms on each side here, so the strength of this is the same. They're going to cancel each other out. When we have a trigonal planar molecule, and we have these are equal in strength, you can see, if this guy's playing tug-of-war and these people are pulling on him, even if they're stronger, okay, he might be in some pain, but he's not going to move, right? Because the forces are opposing each other. Over here, again, we've got 3 people pulling on that central atom, but because it's not symmetrical anymore, it's going to move. This guy's going to move straight down because he's getting pulled on in these different directions, but they're all on one side. It's not symmetrical. If we have a bent molecule like we saw with water, it's going to move. Over here is a tetrahedral shape. Well, that's symmetrical. If all of these are pulling with equal strength in opposite directions, there's no net movement. So the dipoles cancel out. You guys have any questions? Let's do something here. So let's investigate this vector addition thing. So if I have, let's do it this way. If I have a vector that's going like that, we can think of that as being, come on, let me change the color. I need a different color. Oh, there, that's better. That's like this. and this. So it's a little bit like driving in Reedley, where the central of town is tipped on a diagonal. Do you know why so many of our Central Valley towns are like that? They line up with the railroad tracks. They started out by the railroad tracks, and so the streets in the middle are parallel. And I don't know if, I just imagine this happened. They said, you know, this is really stupid. And so the town grew a little bit, and they said, okay, let's just be straight north and south now. So we've got this square in the middle that's tipped, and then everything else is north and south. But if you're going from this point, you can take one of those angled streets, or you can go outside and go at right angles, and you'll get to the same place, right? So in vectors, we've got this direction. This is the sum of that plus this. And so when we see something at an angle like that, we can look at its two parts. So if we have, let's see if I can do this. So if we have another one going in that direction, we can think of that as being this plus this. Is that making sense? I'm going from point A, I'm going here from point A to point B. And I can get there in two ways. I can go straight, or I can go around the block, basically. So when we look at this, and we look at these green arrows, now kind of a sloppy drawing, use your imagination. Those are opposing each other, and those are going to cancel each other out if they're of equal length. You see that? So those add up to 0. Those don't do anything. But the red ones are both going in the same direction, and so we're going to end up with a net movement here, if you want to think of it that way, in this direction. Because the red ones are going to add up and pull in that direction. Now that maybe made sense to some of you and not to others. Hopefully one of those explanations, either the vectors or the tug-of-war thing, would make sense to somebody. If we look at it like this, where we've got this point in the center, and we've got the two arrows going in opposite directions, that's like people pulling on you from one side and the other side. That adds up to 0. It's no net movement. Or if you have two people pushing on you like these green arrows, it adds up to 0. If you have people one person pulling this way on you and another person pulling the same way, that adds up. It adds instead of canceling, and then you've got movement. Any questions? So what we need to be able to do is we need to be able to figure out, is a molecule polar or nonpolar? First of all, you have to identify whether the molecule has polar bonds. So if any of the atoms that are bonding to each other have different electronegativities, then it's going to have polar bonds. And for our purposes at this beginning level, if the elements are different, we're going to assume that it's a polar bond. And then you have to figure out, do those polar bonds add up to form a net dipole moment, or do they cancel each other out? And so you have to use VSEPR theory and look at the molecular geometry and look at, is this molecule symmetrical? And so that's how we've been talking about it. And then there's another way. This is my kind of cheater method for determining molecular polarity. Look at the Lewis structure. You have to do that for the other method anyway, because you have to know the geometry. Look at the Lewis structure. It will be nonpolar if both of these conditions are true. No lone pairs on the central atom, and the atoms bonded to the central are either all the same or they have the same electronegativities. And for our purposes, I'll only ask you, same or different. So let's do some examples. Let's look at CH4. Well, we need the Lewis structure regardless of which method. I'm going to show you my method first, and then we'll look at the other method. So we've got carbon, and the hydrogens are going to be around it, because hydrogens have to be on the outside. And then we say, well, we've got 4 valence electrons on the carbon. We have 4 hydrogens. They each have 1 valence electron, and so that adds up to 8. And so we put our bonds in, and we realize 2, 4, 6, 8, the bonds, there's no lone pairs. There's our Lewis structure. So my method is you look at the Lewis structure there, and you ask yourself, are there any lone pairs on the central atom? Any dots? No. Okay. Are the atoms bonded to the central atom all the same? Yes, they are. Therefore, this is nonpolar. The molecule is nonpolar, even though it may have polar bonds. The other way to look at it is, what geometry does this molecule have? It has tetrahedral geometry because there's 4 electron pairs around the central atom. So then we have opposing forces. All the atoms are the same. We've got vectors going in opposite directions, and they're going to add up to 0, and it's nonpolar. Let's do one other in here. What if one of these was different? Just to be complete, I'm going to show the lone pairs on this guy. That's going to have the same geometry as CH4, right? There's 4 groups around the central atom, so it's going to be tetrahedral geometry. Let's use my rules. Does the central atom have any lone pairs? The central atom, the middle one. Any lone pairs on this guy? No. There's lone pairs over here, but we don't care about that. We're looking at the central atom. Central atom, no lone pairs. Okay, so that's good. Are all of these the same? Do they all have the same electronegativity? No. Chlorine is a lot closer to fluorine than hydrogen is. This is more electronegative. So the first condition is true, the second condition is not true. So then we say this is a polar molecule. So this one's polar. If we're thinking of the other method, the shape is tetrahedral, but is it symmetrical? No, you've got chlorine in there who's really strong, and you've got hydrogens that are really weak. Even if they're pulling in opposite directions, it's not going to balance out. Let's look at NH3. Again, we've got to have the Lewis structure. So the nitrogen goes in the middle, and we get a hydrogen on each side. We've got 5 electrons for the nitrogen, and 3 from the hydrogens, which is 8. And so we put these bonds in here, and then we're going to end up with a lone pair on nitrogen, right? Because we need 8 electrons, and 2, 4, 6, 8, and the nitrogen has an octet, and the hydrogens have duets, and so everybody's happy. And then we ask ourselves, are there lone pairs on the central atom? Yes. We're done. It's polar. It has to be. It's lopsided. Okay? The other method, look at that. Well, what's the shape of it? It's going to be trigonal pyramid because the electron shape is tetrahedral. There's 4 electron groups, but then one of them is a lone pair, and so the shape is trigonal pyramid. It's going to be kind of like this, with this guy sticking out and this guy back there. And so it's lopsided, and it's going to have a net dipole going this way. The nitrogen's going to be negative, partial negative, and the hydrogen end is going to be partial positive. SO2. Let's do this one real quick. Well, we should put the sulfur in the middle and the oxygens next to it. Sulfur has 6 valence electrons. 2 oxygens, each with 6 valence electrons, gives us 18. So we need to put at least one bond in here. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. We ran out. Ran out of electrons, not making everybody happy. So then we have to share a little bit more. So I'll erase 2 electrons and share them instead. Very messy here. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. Now we can determine whether this is polar or not. Are there lone pairs on the central atom? Yes, it's polar. That's easier, huh? I'm thinking about vectors and stuff. If we look at the shape, what shape does this molecule have? Bent. The electron geometry is trigonal planar because there's 3 groups: a double bond, a single bond, and a lone pair. Trigonal planar. And so the oxygen is more electronegative than the sulfur, and so we've got our dipoles going like this, and the overall dipole is going to go like that. And so this end is going to be negative, and this end is going to be positive. Kind of getting a feel for how to predict whether these are polar or nonpolar? So how does this apply to the oil and water? Well, water molecules, we've learned, are polar. So here's an illustration of 2 water molecules. We learned that the oxygen end is partially negative, so the red's negative, and the hydrogen end is partially positive. Well, what happens to opposite charges? They attract each other. This partial negative is attracted to the partial positive, just like the north pole of a magnet is attracted to the south pole. So they're going to tend to want to stick together. That's what polar molecules do. So when you have a mixture of polar and nonpolar molecules, they're going to act a little bit like what's going on in this picture. The solid colored marbles are magnetic, and the more clear ones are glass. So the magnetic marbles are attracted to each other, and the glass marbles are not. And you can throw all these marbles together, and what's going to happen? The magnetic marbles are going to clump up, and they're going to kind of squeeze out the glass marbles. The glass marbles have no attraction for these or for each other. And so they're just going to be kind of rolling around, and these are going to bunch up. Oil molecules are nonpolar. They don't have a positive and negative end. They're very symmetrical. They have basically nonpolar bonds to start with. And so there's no positive-negative charge separation at all. And so what happens with oil and water is here you have the water molecules with their little dipole moments, and they're attracted to each other. And here you have the oil molecules, and they do not share that attraction, and so they basically get squeezed out. They are on the top, not because they got squeezed out, but because their density is less. You can also have nonpolar and polar layers where you have the nonpolar one on the bottom. That has to do with density. But the water molecules are so attracted to each other that they squeeze the others out. It's a little bit like people. You get a group of people that have a lot in common, and you bring in a bunch of other people that have nothing in common with them in a social situation, and what's going to happen? You're going to have these little cliques, these little groups where people are talking, and this other person come in, and you're like, you don't even know what to do with this person. So I'll pick on the Swedes and the Japanese, because I'm full Swedish and my husband's full Japanese, so not being racist. So if you had a room full of people, and you had Swedes from Sweden who didn't speak Japanese, they spoke Swedish, and people from Japan that spoke Japanese. Are they going to mingle real well? Not so well, no. The Swedes are going to tend to talk to each other, and the Japanese will talk to each other because they understand each other. So this polar-nonpolar is a little bit like a language. There's attraction between the polar molecules. There's no attraction with the nonpolar. And here's real quick, this is kind of interesting, about how soap works. Here's a picture of a soap molecule. It's got one end that's polar and a long tail that's nonpolar. So this nonpolar tail talks real well to grease and oil, and it will dissolve in the grease and the oil. And this polar end talks real well with water. And so what happens is these soap molecules will surround some grease or oil with their nonpolar tails in there, and they'll feel all comfortable and everything. But on the outside, you have this polar part that's good at talking to water. And so it's a little like a Trojan horse, and it can carry this greasy stuff through the water and enable you to wash it away. If you get Crisco on your hands, there's no way that water is going to wash it off. You got to get some soap involved. It's not a matter of you didn't wash enough. It just does not dissolve in the water. So then, chapter in review, and we're done. Chapter 10. See you on Wednesday.